Alright, so we're still looking at the cohomology spectral sequence for filtration of a space and trying to make things a bit more precise. And maybe I should have just kept going, but I try to keep these videos a little bit more bite-sized, just because I think it's hard to have the attention span to watch a video for so long. But anyway, let's pick up basically where we left off. So maybe let me remind you that we had this very colorful unraveled exact couple, and this was coming from our filtration, right? XP includes into XP plus 1, and this filters our space X. And of course we have a first quadrant spectral sequence that we're trying to understand how it's really built formally, and that had E1 PQ as the homology of the filtration quotients. And this is supposed to cook up the homology of X. And then we had just defined these co-cycles and co-boundaries. And what did those look like? Well, our co-cycles were elements in the cohomology of our filtration quotient, where you apply K to them and you see that you can lift up the diagram R times. So you must have been in the image of I to the R minus 1. And then our co-boundaries looked like J of things, taking you into this cohomology of the filtration quotient. And then that thing that you had started with was in the kernel of I to the R minus 1. Okay, and what we were just trying to understand is that we have this definition where we let ERPQ be ZRPQ mod BRPQ, but we also know, oops, sorry, that's supposed to be, well, that's fine. I meant to write R plus 1 everywhere. I guess I can fit it. So that's coming from the same definition for ER for all the R's. Okay, but then the story that we know is that this ER plus 1 is supposed to be the cohomology of the rth page with respect to this differential. And that differential, well, let's try to unpack that a little bit. And let's see that these agree. So this DRPQ is supposed to go from ERPQ, which we said is, we're going to take to be defined as ZRPQ. So our co-cycles mod our co-boundaries, BRPQ. A lot of sources leave off the Q's here, by the way, and you might prefer that because they're kind of just in the way, but I like to match the picture that I'm looking at and not have to guess about the indices, so I'm going to write it out in its gory detail. But remember that our differential is supposed to go over R and down R minus 1, so we're going to land in ZRP plus R, Q minus R plus 1, mod co-boundaries in the same place. Okay, and that's our ER P plus R, Q minus R plus 1. Right, so that's just saying what the bidegrees are supposed to be. And we should make sure that this even makes sense. So the first thing to notice is that if X is in ZR PQ, then we look at K of X, okay, and I'm going to keep scrolling back to this unraveled exact couple. So I've got some X here. I look at K of X, and because it's in ZRPQ, it's not just there, but I know that I can lift it up the diagram R minus 1 times, right? So certainly I can do that, lift it up R minus 1 times, and then do J, and that is my differential. So let's just write that down. So we've got KX. This is something that's in the image of I to the r minus 1 by definition of the z's. And so we can define j after I inverse r minus 1 times after k applied to x. Okay, and that's what our dr was supposed to do, right? Dr, remember, looks like, in quotes anyway, do j after I undone r minus 1 times after k. Okay, so that's at least good news, right? These are the things that we can define this map on. But what about this quotient? Well, if we had that x was j of y for something, just trying to say it's something in the co-boundaries, well then we would do this thing to it. That's a subset, so this quotient makes sense. So we can still do this map, and now it's not to x, but it's really to jy, but now we've got that k after j happening, and that's 0. And again, that's somehow hard to remember sort of all the letters, but that's k after j happening in the same color, right, in some long exact sequence, so of course that's 0. Okay, great. So all I'm trying to say is yes, dr does map out of the quotient. It's a good sanity check. Okay, so what I really want to do, though, is find out that taking homology with respect to this differential gives me this same definition that I'm getting from this quotient. So to do that, there are going to be really 2 steps, and I'll talk through the idea of these 2 steps, but the proofs, the formal proof will be an exercise. So the first step, claim 1, is that ZRPQ mod ZR plus 1 PQ. Yes, remember they are nested in that way. Okay, from the last video, that there's a map to BR plus 1, P plus R, comma, Q minus R plus 1. Okay, again, this is why people don't write the degrees. It's just the degrees that it should be for the differential. But then BR, same degree. I really like having there for my own sanity. Okay, so the claim here is that this map is an isomorphism. Okay, and let me say the proof is an exercise, but I'll talk through at least why this is believable if R is 3. Okay, so say R is 3, then we should be looking at Z3 mod Z4, and for the sake of this sort of heuristic argument, let me leave off the details here. So then I should be looking at, whoops, B4 mod B3. Okay, and let's think about Z3 mod Z4. Okay, so I'm going to go back up to my diagram. What is Z3? Z3 are elements here, elements in the cohomology of the filtration quotient that I apply k to them, and I can lift up r minus 1 times. So Z3 I can lift up 2 times. So I take some little x here, and I go over here, and I can lift it up and get something up here, hn of xp plus 2. Okay, what does it mean to be in Z3 mod Z4? Well, that means that I take this little x and I send it over, and I can lift it up twice, but I'm going to kill the things that I could have lifted up 3 times, right? So what do I, thinking about that in terms of our old story of differentials, if I send this over and I get 0, I can lift it up once. So that's if D1 is 0, I can lift it up once. And then I apply J, and so if D2 is 0, then I can lift it up again. And so what that tells me is this class, it supported 0 D2 differential, and then we lift it up, and now we can define D3. But notice, if D3 was 0, then we'd be able to lift it again. And we're killing all that stuff. So I'm just going to think of, I can lift this up twice, but not 3 times. So it must support a non-zero D3 differential. Okay, so let me come back down here and kind of, well, okay, maybe let me not write it in the interest of not wasting your time. You have this on video, so you could write it down if you want. Okay, so that was something that we could lift up whoops. Come on. Okay, we could lift it up twice, but not 3 times, right? So it supported a non-zero D3 differential. Now I want to compare that to B4 mod B3. So let's go back up here. What is B4? Well, B4 is things where I have J of Y in the homology of the filtration quotient such that that Y is in the kernel of doing I R minus 1 times. So notice, by the way, that those B's, I didn't write them the second time, but they should have those shifted P's and Q's. So maybe let me think about something here. It's supposed to be something where I have some Y goes to J of Y, and then I ask how many I's kill it, right? So if it's in B4, then applying I 3 times should kill it. I should be in the kernel of I to the R minus 1. And if it's in B4 but not B3, that means that sending it down twice shouldn't be 0. Okay, so let's just think about what happened in our old story of doing differentials. So we have this class Y and it goes to J of Y, and that looks like the end of a differential happening. If we pushed it down 3 times, we got 0, but not when we pushed it down twice. Okay, so that means there's a non-zero class here that goes to 0. Oh, but in the orange long exact sequence, that means there's something here that maps to that thing. Okay, and what would our differential do? It would take that thing, it would map to it, it would lift it up the twice that we know we can do and send it over. Okay, so that thing just supported a D. Oh, I think I've got my indices wrong. Hold on here. No, I'm just counting wrong. So that was a D3 differential that I just pointed to, but I think I said D2. Okay, so all of that is to say that, yeah, we knew this thing was coming from a D3 differential from our other story, right? What does it mean to be in B4 mod B3? That means that we don't support any D2 differentials, right? Well, Okay, so now what's key is that D3 differential that we were looking at from our old perspective of Z3 mod Z4, that D3 differential is supposed to be non-zero, right? Well, that's going to happen when we do this lifting and all of those stages are non-zero. But if we had a D2 differential coming into here, it would have gone through that stage. So what I'm trying to say is that we have B4 mod B3 in the sense that we know this D3 differential is non-zero, so it couldn't have been something that was hit by a D2, something in B3. Okay, hopefully that sort of made sense and I did not twist the words too much. Again, it's an exercise to prove this claim more precisely. Of course, you're going to want to write down, in fact, the map, but there's our heuristic argument. The other piece that we need here is claim 2, and that's that dr, the differential, factors in a nice way, and we'll use this claim 1. So we know it's supposed to go from ZRPQ mod BRPQ, just because that's our ERPQ. And it's supposed to go to, well, ZR mod BR again, but now I didn't leave myself enough room. P plus R, Q minus R plus 1, that's just coming from the degree of our differential. BR same thing, P plus R comma Q minus R plus 1. That's our ER in that degree. Okay, that's what our dr differential is supposed to do. So the claim is that this factors as the quotient to ZRPQ mod. Well, BRPQ lives inside all of the Z's, right? And the Z's are nested, so I can quotient by ZR plus 1 PQ. And now notice that term showed up in our claim 1. So now I want to use that isomorphism to BR plus 1 P plus R Q minus R plus 1 mod. Should have just copied and pasted, but we're almost done. Okay, so that's just using the isomorphism of claim 1. And then here, I'm just going to use the inclusion. So notice the quotiented terms are the same. So I'm just using the inclusion, again, of the co-boundaries into the co-cycles. Okay, and the claim is that this really does factor dr. Again, let me say the proof is an exercise, but we can talk through it roughly. So somehow, the isomorphism and the inclusion is maybe not doing anything so weird. We've already talked through claim 1, and this inclusion is just include. But what are we doing here in the quotient? So we want to take these co-cycles mod co-boundaries and send them to co-cycles mod other co-cycles, right? So we want to look at things where we look at kind of the stuff that supported non-zero differentials, kind of like we were just talking through in claim 1. Okay, let me not say too much more because I'll certainly just twist up my words. And to be frank, you've probably just got to go through it yourself. But notice, what do we get for the kernel of this differential? Well, on the face of it, it's maybe not so obvious what it should be. And I mean, we've chased things through the unraveled exact couple. So we've talked a little bit about what this kernel looks like. But now with this nice description of this map that factors, well, we really see that what's the kernel? The kernel's just going to come from this first piece, that quotient. Okay, so it's precisely these co-cycles that we quotient by mod the quotient term before, right? So, okay, great. And then what's the image? Well, again, chasing it through this diagram, the image are all the things that we hit. So we're surjective here, and then isomorphic here. Okay, so this is the image as it lives inside this other thing, but I'll just say it's isomorphic to that. Okay, so, well, that's a little bit weird. How does that help us at all? Notice that when I'm doing this, I'm talking about the dr differential coming out of the PQ spot. But what I really want to think about when I think about kernel mod image is coming out of the PQ spot and coming into the PQ spot. So in this image story, let's replace P with P minus R and Q with Q minus R plus 1, just so that we're landing in the PQ spot, right? And that's going to tell us that really our kernel, maybe I'll do it this way, the kernel mod the image is, well, the kernel was ZR plus 1 PQ mod BR PQ. I don't need to change that one, right? I was going out of the PQ spot, but now I want to come into the PQ spot, so I'm going to change that image, and we'll change it to, well, when we do that, we're going to be getting r plus 1 down here still, but now that'll become p, and that'll become q. And then I think I said this backwards. Sorry, this should be q plus r minus 1. The whole point is to get pq. So yeah, I think that's better. Okay, anyway, the point is you should be sort of blurring your eyes and not paying too much attention to the indices anyway, but I always like to at least try to be careful and believe that this will all work out. Okay, well now I just need an isomorphism theorem to cancel these quotient terms, so I'll get zr plus 1 pq mod br plus 1 pq, and the whole point of this story is that yes, that really is er plus 1 pq. Okay, so it's all checking out, and the whole point is that yes, we do have a spectral sequence using these very carefully defined co-cycles and co-boundaries, and we know how they relate to each other. We can define the ER page, we can define the ER plus 1 page. Yes, our intuition of the ER plus 1 page is just the cohomology of the R page with respect to this differential. That is all still true. We have not, we've only changed our perspective, but that all still holds. And we now defined really precisely what the E infinity term is. Remember that our E infinity term was just take Z infinity, that was the intersection of all the Z's, mod B infinity, that's the union of all the B's, and the B's sit inside the Z's, so okay, that quotient makes sense. And now the question, which to some degree will take us a lot to answer, but we can at least start to answer soon, is how does this all relate to the E infinity term? Right, so now we know, yes, we have a spectral sequence where the rth page behaves as we expected. All of the rules that we were following, yes, do make sense. But the whole point is, what does this converge to? What does this E infinity term mean? What does it tell us about? How does it tell us that? And so on. Okay, so that's where we'll head next.